Hi there. In Lesson 8 today, we're going to explore the n+1 principle. We've seen in earlier lessons that we could define a line if we had 2 points. We could define a parabola with 3 points, and we could fit a cubic function to 4 points. In the n+1 principle, we're going to look at finite differences and use those to solve some real-world applications. So the property of finite differences says if we have a polynomial whose degree is n, then the nth order differences of the function values for equally spaced x values are non-zero and constant. Conversely, if the nth order differences of equally spaced data are non-zero and constant, then the data can be represented by a polynomial function of degree n. So it's this second statement that we're going to look at in our first example. Triangular numbers can be found by using this pattern 1/2 times the quantity n squared plus n. And if we look at these figures here to the right, you can see that when x is 1, the f of n is 1. And when x is 2, the f of n is 3. When x is 3, the f of n is 6. And when x is 4, the f of n is 10. So the finite differences, the difference between 1 and 3 is 2. The difference between 3 and 6 is 3. And the difference between 6 and 10 is 4. These are the first order differences. Now, if we subtract those differences again, you're going to see what is meant by the definition that the x values are non-zero and constant. So here the difference between these three figures is 1. So 1 is a non-zero number, and they are constant since 1 is the same number in both differences. So in our second order differences, because they're non-zero and constant, it can be shown, as stated, that the function f of n is a second degree polynomial, 1/2 n squared plus 1/2 n. So in example 2, we want to use that property and notice that the difference between 16 and 31, 31 and 46, 46 and 61, and then 61 and 76 are first order differences, and x to the first power is a linear function. So our first order differences can be written as a linear function. So if we took the slope between the first 2 points, let's say 31 minus 16 divided by 6 minus 3, we find that the slope is 5. So the rate of change is 5. And if we considered what would happen when the years were 0, if we went backwards 15, then we would be at 1. So this would be our b value of 1. So writing that linear function as y equals mx plus b, or ax plus b, then our linear equation could be modeled by the equation y equals 5x plus 1. In example 3, we're going to use what is known as the n+1 property. So here we're given a quadratic set of data points, and we want to fit a quadratic model to that. So we're going to use this general form of a quadratic and pair those and write a system of equations using ax squared plus bx plus c, and then that's going to be our y value. So in this first one, our x value is -1, and our y value is -2. If we repeat that process using 0, -9, and 1, -12, we'll come up with a nice set of equations, and they're going to simplify And in simplifying, if I label these equations, equation 1, equation 2, and equation 3, you can see in equation 2 that the c value is -9. So using that information, we have a minus b plus c is -2. We have c is -9. And we have a plus b plus c is -12. And using the fact that c is -9, if we substitute here and here for these two c values, we'll get a minus b minus 9 is -2. And we'll get a plus b minus 9 is -12. That's going to simplify down to a minus b is 7, and a plus b is -3. Solving for that system, we see that our a value is 2. So we know a is 2, and c is -9. And if we substitute here, 2 plus b is -3, then we'll find that b is -5. And we already knew c was -9. So fitting our n plus 1 property into that quadratic model, we have the equation y equals 2x squared, because a is 2, minus 5x, because b is -5, minus 9, because c is -9. Now in this example, we're going to take this set of data here, and I'm going to model with my TI Inspire, substituting these data points into my list and spreadsheet. I'm going to create a list of the data that's going to look something similar to this on my calculator. And then I'm going to use the stat and the calc feature. So I'm going to go stat calc, or let's see, stat calc if we had the TI-84, or with the Inspire we're going to go insert data and statistics. So depending on which calculator you're using, I'm familiar with the TI family. So on mine with the Inspire, I'm going to use the data and statistics, insert data and statistics, and line up the X values, and then line up the Y values, and it's going to give me this nice smooth curve. Next, we want to analyze the data, and in this picture for the lesson, I chose the quadratic model because it kind of appeared to be quadratic in nature. I also, in a separate screen that I don't have on the notes, I also found an exponential model. So we're going to record those here. So my quadratic model was y equals 428.7 x squared minus 1104.5 x plus 1309.2 on the constant. And you could see that that data was listed across here. Now the exponential model, again, I don't have that graph here to show you, was 285.32 times 1.875 to the x power. So for this particular example, I'm using the quadratic model. You might find the calculator convenient when given tables of data. In example 5, it's another chance to find a polynomial function that gives the number of diagonals of a polygon with insides, and we're going to use the model to determine how many diagonals on a 12-sided polygon. So the first thing we have to do with this data, either go back and create a model like we did in example 4, or I'm going to use, in this case, I'm going to use the n plus 1 rule and I'm going to find my differences. So the difference between the y values as x increases by 1 is going to be a step up of 1 in each case. So that would be the first differences. And then I notice the differences, the second differences are all 1. So it's going to be a quadratic model. And if we use that n plus 1 rule, I can say using ax squared plus bx plus c is my y value. Using this amount, I've got 9a, because my x is 3, so 3 squared is 9a plus 3b plus c is equal to my y value. And then moving on into the next ordered pair, 4 and 2, we're going to get 16a plus 4b. So 16a plus 4b plus c is going to be 2. And then in the next set of data, 5 squared is 25a plus 5b plus c equals 5. So using this system of equations, I can solve that system and come up with my function, the diagonals in terms of the number of sides is 1/2 n squared minus 3/2 n. Now I did not have room here to show that I solved A was 1/2, B was negative 1/2, and C was 0. So I'll save that exercise for you. And substituting to answer the question, how many diagonals on a 12-sided polygon, by substituting 12 into our quadratic model, we found out that there are 54 diagonals in a 12-sided polygon. For example 6, if we put all this together, you should be able to use your particular calculator and substitute these values into the calculator and find, either with the spreadsheet or the modeling tool, that you can write a quadratic model and a cubic model. So my quadratic model on my Inspire turned out to be this equation, and my cubic model, using the same calculator, turned out to be the equation shown here. Now we could be off a little bit if you're using the TI-84, but it should just be in the hundredths. And if you check those models using the spreadsheet and looking at the scatter plot, it appears that the cubic model has the best line of fit. It seemed to hit the ordered pairs the closest. So use our model to find the number of vehicles that pass through the intersection at 5 p.m. each day. So 5 p.m. would be when t was 17. And that's the 5 p.m. time. And by substituting v equals 17, I substituted into my cubic model, I found out about 85.86. So that tells me at 5 p.m., about 86 vehicles are going to pass through that intersection at that time. Okay? And then in our last example, we're going to look at a jet ski's average speed, and that's given in y, and y is in knots for several engine speeds, and the x value is in hundreds of revolutions per minute. That's RPMs as shown. So when I look at this table, I'm looking for first differences, So my first differences are a variety. They're all really close to, they're very close to linear until we get to the last two. That's a little off. When we look at second differences, we got 0.23, 0.99, and then we go negative 1.9, and this one's still off. Third differences, and so I couldn't find anything that looked really clear, but I did look at the scatter plot, so I'm going to make a note of that. And I don't have that picture to show you, but the scatter plot appears to be cubic. So we're going to go with the cubic model as the best fit, even though these are kind of off. And I believe it's this number out here that's the outlier throwing that off. So part A, we want to find a polynomial model for that data. And again, I used the table on my calculator and made a scatter plot and then fit the scatter plot. So I came up with 0.00495 behind the decimal for my cubic and 0.1519x squared and 3.274x and minus 10.037 for my cubic model, again using my calculator. So if I use that model to estimate, I'm going to substitute 25 when the 2500 RPMs, so 2500 RPMs is asking me to evaluate 25 since they told us it was in the hundredths. So the y of 25 inside this equation up here, so we're going to substitute 25 for x cubed, 25 for x, and 25 here. So in each case, we're substituting 25. That turns out to be 54.22 knots. And if you convert that, 54.22 knots is roughly 62.4 revolution or miles per hour. And then lastly, on part C, they're asking us what the engine speed would be. What engine speed will produce a jet ski speed of 20 knots? So that question is asking us what is the x value when the y value is 20? So that happens when x is about 14.2 or 1420 RPMs. That's when the jet ski speed will be about 20 knots. And the way I did that was I took the equation on my calculator and found out when x was 14.2, y was 20. So I was looking at that equation where that crossed on the cubic. And this is the end of lesson 8 in chapter 5.